Hello everyone, I hope you are doing well, and today we are going to discuss carbonyl compound, which is very important because in DAT we have a lot of questions from reactions, from name reactions, as well as oxidizing and reducing agents. So a lot of variations in this chapter. Okay, so let's start the very first one. So first of all, I would like to discuss what we have to cover in this chapter. So look at here. In carbonyl compound, so first we are going to learn a very important reaction which is called nucleophilic addition. Nucleophilic addition. Second, oxidation and reduction of carbonyl. And third, name reaction. Few name reactions like Wittig reaction, okay. And the fourth one is reaction with amine Grignard and organometallic compound. So these things we have to cover. Carbonyl is what? Carbonyl means C double bond O. Okay, this is called carbonyl, and in this chapter we are going to cover the reactions of aldehyde and ketone. As well as we will cover few more things related to aldehyde and ketone, like its reactivity. Okay, so let's start the very first one. Few important structures in this chapter, like this one. So if you are going to talk about structures of carbonyl, this one HCHO, the general name is also very important, which is called common name. This is called formaldehyde. Also in IUPAC system it is known as methanol, because just one carbon we have. So one carbon is my principal chain, and we all knew aldehyde is like al. Okay, this is very important, CH3CHO. This is called as acetaldehyde. And this one CH3COCH3, this is called as acetone. And this is ring, and we have CHO group. This is called as benzaldehyde. Okay, so these 4-5 structures are very important and very common, because sometimes it can be a direct questions like what happens if you are going to reduce benzaldehyde, or what happens if you are going to oxidize acetaldehyde. Make sense? So these structures are very important. So this is the structure of carbonyl. Carbonyl means C double bond O again. Clear? Let's talk about a very important reaction which is called as nucleophilic addition. Before starting this reaction, we should know what is the structure and property of carbonyl. So look at here, this is my carbonyl bond. This is a carbonyl bond in which oxygen has 2 lone pair and this carbon. So if you look at the hybridization state of this carbon, it is sp2. And this oxygen is also sp2. Why? Because this one has 3 electron pair, 1 lone pair, and 1 bond pair from double bond. Okay, we all knew sigma bond takes part in hybridization. So this one has 1 sigma and 2 lone pair, overall 3 electron pair, which means sp2. Clear? And if you are going to break this one, why we are going to break? Because oxygen is delta negative and carbon is delta positive. So it is going to break like this, and this is the resonance structure of this. Clear? So as you can see, oxygen is a more electronegative, so it will pull the electron of the carbon. So carbon becomes electron deficient. So this carbon is called as electrophile, and this oxygen is known as nucleophilic carbon, oxygen, nucleophilic atom. Make sense? And this is a planar structure. So this is just a structure of this carbonyl one. I'm going to write here is structure. Okay. So this is a planar as well. CO molecule is a planar one, especially the carbon oxygen bond. So suppose this is a plane, okay, and this is the black one is my nucleophile. If this structure is a planar, so this nucleophile has two possibility for the attack. It can be either top of the plane, or it can be below the plane like this, because this is a planar geometry, the carbonyl one. Clear? So if I'm going to talk about the nucleophilic addition here, suppose we have this aldehyde molecule and we have a nucleophile here. So this carbon is a electrophilic carbon and this oxygen is a nucleophilic atom. So nucleophile is going to attack on the carbon of this CO bond, because this is electrophilic in nature. Okay, a reaction can be good if we have a strong nucleophile and a very good electrophilic carbon. So the attack is very good. Okay, so this carbon is electron deficient, that's why electrophile, and this we have a nucleophile. So this is going to attack on this carbon and this bond is going to break. So as a result of it, O negative, here H, and here we have a nucleophile. In the next step, it is going to protonate from any H plus. It can be from any acid, it can be from water. Okay, so O minus going to grab this proton, so it becomes like this. Clear? So this one is a sp2 hybridized here carbon, and this is sp3 hybridized. Clear? So this reaction is called as nucleophilic addition. A lot of reactions, in the nucleophilic addition, like reaction with Grignard. I can give you an example of Grignard. Look at here. We all knew, suppose we have this aldehyde and we are going to use a RMgX here, suppose R dash mgx, and the next step we have water. So this is the first step, this is the second step. So as you can see, this is a electrophilic carbon and we have a nucleophile R dash, so it is going to attack on this carbon and this bond is going to break. So as a result of it, it will be O minus, and here we have R dash and this is H. And in the next step we have water molecule, so O minus is going to grab this proton, so it will be RC, here OH, here H, and here we have a R dash. Makes sense? So this is reaction with Grignard, which is an example of nucleophilic addition. Clear? Okay, let's discuss this slide. So this is talking about the oxidation of alcohol into carbonyl. We all knew if you have a primary alcohol, it can oxidize to give you aldehyde, and aldehyde further oxidize to give you acid. Let me explain this. Look at here. Suppose I am going to start with the primary alcohol. This is called 1 degree alcohol. And if 1 degree alcohol is going to oxidize, it will become aldehyde. Clear? And aldehyde further oxidized to give you acid, RC double bond OH. Clear? So this oxidation from primary alcohol to acid is carried out by a strong oxidizing agent. And if you have to stop the reaction at aldehyde from primary alcohol, this is mild oxidizing agent, clear? So we can categorize the oxidizing agent in two parts, a strong as well as mild one. So this is the story of primary alcohol. Suppose we have secondary one like this one. Secondary alcohol is going to oxidize into ketone, and we can use both here, means a strong as well as mild oxidizing agent. Both can oxidize secondary alcohol into ketone, clear? So now we should know what is my strong and what is my mild one. So I am going to categorize here. Look at here. The strong oxidizing agents are K2Cr2O7, and we can use KMnO4 as well, KMnO4 in acidic medium H+, okay, like H2SO4, with H2SO4. This is the first one. Second, we can use CrO3 with H+. So these two are very common one and very important. So once we are going to take KMnO4 with H+ or acidified KMnO4 or acidified CrO3, it can convert primary alcohol into carboxylic acid and secondary alcohol into ketone, clear? Now mild oxidizing agents are, the very important one is a PCC, which full name is pyridinium chlorochromate, as well as we can use only CrO3 without H+, without acidified condition. So these two are very important and we can use both of them in mild oxidizing agent. So this is the oxidation of primary alcohol and secondary alcohol, and we can form aldehyde and ketone. Make sense? So now the next one is reduction. Reduction of carbonyl. So look at here. Suppose we have acid. Acid further, if you are going to reduce acid, it can form first aldehyde, and if you are going to reduce aldehyde, it can be primary alcohol like this. And if you have a secondary alcohol, it can give you ketone, clear? This is the reduction. And if you are going to use a strong reducing agent, it can convert primary alcohol into carboxylic into primary alcohol directly, and that is a strong reducing agent. I will cover oxidizing and reducing agent individually, but here these are the important ones, so I am going to discuss some of the like a strong reducing and mild one as well. If you are going to stop carboxylic to aldehyde, we can use mild reducing agent, clear? A strong reducing agent very common, which is my LiLH4, clear? And the weak one is NaBH4, sodium borohydride, clear? Both LiLH4 and NaBH4 is going to donate hydride ion as a nucleophile, and this reaction is a nucleophilic addition. I can tell you example. Look at here. Suppose we are going to reduce aldehyde. The very first step we are going to use LiLH4, and the second step is water hydrolysis. So how we can do this? Look at here. I said that LiLH4 generates H- as a nucleophile, and this reaction is an example of nucleophilic addition. So what will happen? Nucleophile is going to attack on this carbon, this is going to break. So as a result of it, we have O-, here we have H, here we have H, and in the next step we have water. So O- is going to grab this proton and it becomes alcohol. Clear? This one. So this is a nucleophilic addition with allyl H4, and same process with the NaBH4 as well, because NaBH4 can donate H minus. Clear? So this is a reduction reaction. So as you can see, this is oxidation one, and we can use PCC, which is called pyridinium chlorochromate. And the next one is DMSO. We can use DMSO with COCl2 and NET3 as well. This is also a weak oxidizing agent, and that gives you aldehyde. And if you are going to use KMNO4 or H2CrO4 or CrO3 with acidified condition, it can oxidize the aldehyde into carboxylic one. So you can see primary directly acid from a strong oxidizing agent, and strong oxidizing agents are what? Which one? You can see strong oxidizing agents include KMNO4, chromic acid, and this one as well, Jones reagent, CrO3 with H plus. Clear? This is called Jones reagent, which forms chromic acid in C2. So this is about the oxidation one. Now look at this one. This is the reduction one. We have done this one as well. You can see NaBH4 is a weak reducing agent. You can see here NaBH4 is a weak reducing agent. Ketone reduces into secondary and aldehyde reduces into primary alcohol, and we can use both allyl H4 as well as NaBH4. And the next one is ester and carboxylic. Look at here. If you have acid and ester, if you want to reduce it, you have to only use allyl H4. Do not use NaBH4. Okay. Look at here. If you have ester and carboxylic, always use allyl H4. It can reduce them into primary alcohol. Clear? And if you are going to use NaBH for them, then it is not going to make any reaction. Okay. So ester and carboxylic, we have to always use a strong reducing agent, which is my allyl H4. Clear? We have done this one as well. This is the oxidation of secondary alcohol into ketone. We have done this, and we can use which one? Strong as well as mild, both. Okay. So PCC as well as K2Cr2O7 or CrO3 with the H plus. Now this one is a very important one. I am going to write here. Look at here. There is a reaction called Clemmensen reduction. Look at here. If we have a CO bond, we can convert them into CH2, and we can use two reagents. The very first one is called ZnHgHCl, and second one, or you can use NH2 OH-N. Okay. So both is going to reduce the carbonyl into CH2 group. This is very, very important one. Suppose we have CH3CHO, and if we are going to use suppose here ketone one, and we are going to use here ZnHgHCl, so CO becomes CH2, so we can directly convert into propane. Clear? So this is the use of this is called Clemmensen reduction. This one is called Clemmensen reduction. And the last one, this one is called as Wolff-Kishner reduction. Wolff-Kishner, Kishchener. So Wolff-Kishner reduction, both are very, very important. Okay. Okay, now the next one is this one. Look at this page. Acetyl and ketyl formation. So you can see, look at here. If we have aldehyde, suppose we have aldehyde and we are using alcohol molecule. So aldehyde, when they are going to react with alcohol, it forms hemiacetal. If you are going to use just 1 mole of alcohol with aldehyde, it will form hemiacetal. And if you are going to react again with the alcohol, it will form acetal. So simple thing is that, look at here. Suppose I am going to start with aldehyde with the alcohol. First mole, okay, so it will form structure A, and if A is again going to react with alcohol double dash, it will form B. So A is my acetal and hemiacetal, and B will be my acetal. If we are going to start the reaction with the ketone with alcohol, it will form A, and if you are going to react them again with the alcohol, it will form B. So this A is called hemiketal and this is called ketal. Clear? So simple thing is that whenever you have a product acetal, it means starting material is aldehyde. And how can you memorize this? Look at here. This A in starting, and last we have al, it means aldehyde. And look at this ketal, starting K, it means it originates from ketone. Clear? So, and how can we draw the product directly? Look at here the trick. This is a nucleophilic addition type reaction. Suppose we have this aldehyde molecule and we have alcohol here. So look at here one more thing. If I am going to discuss the mechanism of this reaction, so I personally believe in DAT, there is no need to know the mechanism. You should know only how to draw the product directly. Okay, I can discuss the mechanism, there is no issue. So if you want to know the mechanism, this reaction is carried out in presence of acid. Suppose HCl we have. Okay, why acid? Because this alcohol is a weak nucleophile and it is not going to attack directly on the carbonyl carbon. Whenever you have a weak nucleophile, what is weak nucleophile? Lone pair containing species are considered as weak nucleophile. Okay, so this is one is a weak nucleophile. So first this oxygen is going to protonate in this way. So HCl is an acid, so it will donate a proton. So it is going to protonate like this. Now you can see, due to the presence of positive charge over oxygen, oxygen is going to pull the electron of CO bond. So this carbon is become more deficient. So this is a very good electrophilic center. And now this alcohol is going to attack as a nucleophile. And this bond is going to break. So as a result of it, RC, here we have OH plus, here we have O plus H and R like this, and here H. Clear? In the next step, what will happen? Tell me. Sorry, this positive charge is not going to be here. Look at here. Because once you are going to break the bond, this positive charge will become neutral. The reason is that, look at this arrow. So plus we have already, and arrow means electron. So plus and this electron cancel out. So net charge will be here, nothing. And in the next step, you have H and O positive. So H is going to neutralize this charge over oxygen. So it will be RC, here OH, here H, and here OR. So you can see this is called hemiacetal. So whenever a carbon has two oxygen linkage like this, then it can be either hemiacetal or acetal or ketal or hemiketal. Clear? Whenever such a linkage like this, oxygen, two oxygen connectivity. So what is hemi? Hemi means presence of OH group. Suppose here we have OH here. Again we have two oxygen in which one oxygen is a OH group. So it means now it can be either hemiacetal or hemiketal. Clear? So it depends on the bond of these, these two bonds will decide. Suppose U originates from aldehyde, so it will be hemiacetal, and if my parent is ketone, then it will be hemiketal. Clear? This is the mechanism. Now I am going to discuss the trick. Look at here. This is aldehyde and we have this alcohol, suppose, or even you have ketone. There is no need to know the mechanism. Look at here the basic thing. So oxygen in nucleophilic addition, we all knew nucleophile is going to connect over the carbonyl carbon and hydrogen with the oxygen like this. This is CO bond and here you have a nucleophile and here H plus. Okay, so nucleophile connect with the carbon and oxygen with the proton like this. Same here, if you are going to break this alcohol bond, we all knew this is plus, this is minus, and here as well minus and plus. Now you have to attach these species. This is delta positive, this is delta negative. So you can see opposite charges attracts each other. So carbon is plus, so oxygen with R dash is my minus. So my product will be what? R C O, here OR dash, and here we have H, and oxygen grab this hydrogen, so OH like this. Makes sense? Same here. Oxygen, this proton and this bonded here. Clear? So this is ketone, so it is hemiketal. This is aldehyde, so this is hemiacetal. If we are going to again use another alcohol, simple, eliminate this OH as well and attach this OR group. So you can see OR, H and OR dash. This is called acetal. And look at this one. If we are going to use again another mole of alcohol, suppose double dash, then remove this OH and attach OR dash, so RCOR dash double H and sorry, this is my R. This is R, okay, because ketone is this. So here R and here OR double dash, OR dash like this. So this is ketal and that one is a acetal one. Makes sense? So this is a reaction of aldehyde with the alcohol and ketone with the alcohol. You can see this is hemiacetal, this is hemiacetal. And why this is hemiacetal? Because this one has carbon and 2 oxygen linkage. One side is R and one side is H. R means, and one side H, it means starting material is my aldehyde. We have OH as well, so OH means hemi, so that's why hemiacetal. And here look at this carbon has both R group, it means starting material is ketone, and this is OH, so hemiketal. Clear? And this is the reaction in the basic medium, which is quite simple. This is nucleophile attack over this carbon, this bond is going to break, so O minus in the next it will going to protonate and that forms OH and OR. Clear? And this is a acetal and this is a ketal one. Now the next, this is again the same thing. There is no need to know the mechanism. I already discussed this with you. Whenever we have 2 mole of alcohol and starting material is aldehyde, so it will form acetal. If you have just 1 mole of alcohol, then it will be hemiacetal. If we have starting material ketone and we are going to use a very first mole of alcohol, it will form hemiketal. And if you are going to react with another mole of alcohol, it will be ketal. Clear? So this is all about here. You can see starting material is my ketone. This is the first mole of alcohol. So here you have hemiketal and then finally you have ketal because there is another mole of alcohol here. Make sense? This is in acidic condition. There is no mean of this. Acidic and basic both gives you the same product. Okay, both gives you the same product. As you can see, aldehyde 1 mole of alcohol, so hemiacetal, and if you are going to use another mole, that will be acetal. So you can see predict the product of acetal and ketal formation. Simply swap the carbonyl oxygen of 2 alkoxy group aqueous. Acid can be used to convert acetal ketal back into the aldehyde ketone. This is very important. This one means if you have acetal or ketal and you are going to use a hydrolysis, then it will gives you the starting material. Okay, this one, aldehyde, reaction will be back to the aldehyde. And if you have a ketal and we are going to hydrolyze this, then it will become ketone. Makes sense? Simple thing is that you have to remove this R and R, just attach a CO bond simply like this. Here as well, remove this R and R during hydrolysis, so it will give you H double bond O. Clear? In this way, I can discuss with the example. Suppose we have this aldehyde and we are going to react with the alcohol, suppose 2 mole, and then in acidic condition. Okay, so it will form RCH, here R dash, here R dash as well, OR dash, sorry OR dash, OR dash like this. And now I am going to hydrolyze this. So I said that whenever you are going to hydrolyze this acetal, you have to remove the R part, this R dash and this R dash. So you have just COO, which means C double bond O. So as you can see, RC double bond O and H. Clear? Same thing we can do with the ketone. This is very important, the protecting group. Look at here. I can discuss this one in this way. Suppose you have a ketone molecule and we are using this diol, CH2OH, ethylene glycol also called as. Clear? So simple thing is that suppose you can write ketone in this way and we have this diol in this way. Clear? Whenever you have such a type of thing, always connect in this style. Now eliminate the water molecule. So this oxygen and this 2 hydrogen we can eliminate. So what will happen? This carbon is bonded with this oxygen and this carbon is bonded with this oxygen. So simple thing is that CH3, oxygen, and this is CH2, this is CH2, and like this. Clear? And if you are going to hydrolyze this, it will again gives you the starting material. Simple. Makes sense? You have to just remove the R part. This is the R part, this is the carbon part, R part. So you have to just remove the R part and you can see starting material has double bond oxygen and you can connect like that. This is very, very important in conversion. Suppose we have this and this, and we have this product. Clear? I think we should wait. Give me 1 second. Okay, look at here. Look at this, and I am using here LiLH4. Okay, we have to convert this reaction A into B, and you have LiLH4, you can use NaBH4, or simply you can just convert them in this way. Now look at here. Now you have few reducing agents. If you are going to use LiLH4 is a strong reducing agent which can reduce this ester molecule, as well as this ketone, both. So ketone will be secondary and ester will be primary. But here reduction of ester is fine. Means ester can be reduced by LiLH4 but not NaBH4. Makes sense? So we can use definitely LiLH4, but the problem is if you have LiLH4, then ketone becomes secondary alcohol and here ketone remains unchanged. So how can we convert this? So first of all, we can protect the ketone molecule and we can use a protecting group which is diol, this ethylene glycol, this one. Clear? And if you are going to react this molecule with CH2CH2OH, it can protect the ketone in this style. Look at here, oxygen, oxygen and 2 carbon like this. And ester you can draw in this way. Clear? And now we can use LiLH4. LiLH4 is going to convert this ester molecule into primary alcohol. Clear? This is cyclic ketal. So we can break the cyclic ketal into ketone. Which step? Hydrolysis. So if you are going to use a hydrolysis, we can revert the cyclic ketal into ketone because it is an elimination of this R part. So we have just oxygen and we can see we have ketone. Makes sense? So this is all about the protecting group, which is very, very important. Here we have some examples. You can see this conversion. You can see this one. We have aldehyde and we have ester, and you can see here aldehyde remains unchanged and this ester becomes primary alcohol. So we can use LiLH4, but before using of LiLH4 we can use ETOH, which is called ethyl alcohol. So ethyl alcohol is going to protect this aldehyde like this, and then you can use LiLH4. It can convert into primary alcohol, and after that you can use hydrolysis. So hydrolysis will eliminate both R part. R is what? ET. So you have just oxygen. Clear? And this is the ketone one. This is diol, ethylene glycol. We have done this and it forms a cyclic ketal. Clear? Now this is imine and enamine. Look at here. Imine reaction is a quite simple one. Imine is a easy one. Let me read this. A primary amine has one alkyl group bond to the nitrogen atom. When aldehyde and ketone react with the primary amine in the presence of catalytic acid, an imine is formed. A secondary amine has two alkyl group bonded to the nitrogen. When aldehyde and ketone reacted with the secondary amine in the presence of catalytic acid, enamine is formed. Imine have CN double bond, whereas enamine have CC double bond, and nitrogen single bond to one of the alkene carbon, then name is enamine. Okay. So let me explain the mechanism of ketone with the primary amine. So look at here, it is quite simple. Suppose you have this aldehyde. Suppose we have this aldehyde and we have this primary amine. What should be the product? Do you know what is primary and secondary amine? Look at here. When nitrogen is directly bonded with one carbon chain, this is called 1-degree amine. And when nitrogen is bonded with 2 carbon chain, this is called as secondary amine. And when nitrogen is bonded with 3 carbon chains, this is called as tertiary amine. So in this reaction, we can eliminate the water, oxygen and these 2 hydrogen. And now you have to connect carbon with the double bond nitrogen. So you have this product RCH double bond N CH3. Clear? Makes sense? This is imine. Suppose you have this one, a cyclic ketone. and we have this this one. What should be the product? Again, very simple. C, like this, elimination of water. We have double bond N, nitrogen has 2 carbon, like this. Clear? This is primary amine. And now we are going to do the secondary amine. This is the reaction with the primary amine. There is a mechanism, but there is no need to know the mechanism, okay? There is no need to know the mechanism. Let me discuss the secondary one. Suppose we have this ketone and we are going to use this one, NH here, R and here R. So simple thing is that first of all you can eliminate this oxygen with this nitrogen, remove these two and connect the oxygen, connect the carbon with the nitrogen like this. Okay, now simple thing is that you have to shift this double bond in the neighboring carbon chain, the alpha position. So simply we can say in this way. Here we have, clear? So this is the final product, carbon double bond carbon and with the single bond nitrogen. This is enamine, okay? Means first eliminate the OH group, keep a double bond and then shift the double bond in the alpha position. Alpha is what? Neighboring position to the C double bond N, clear? This is the neighboring, either this or this, both are alpha. Now organolithium one, look at here. This is quite simple. You have to use this one as a nucleophilic addition type reaction. What is organolithium? Whenever lithium is bonded with a carbon chain, that is called as organolithium, okay? Like this one, suppose we have a reaction like we have aldehyde and we are using CH3Li. The first step, second step is a water. So CH3 is my nucleophile, there is no doubt about it. So this reaction will be like nucleophilic addition. So nucleophile is going to attack on the carbon, CO bond is going to break. And the next step is workup. We can use water, it can donate the proton. So O minus grab this proton and we have this alcohol, okay? This is secondary alcohol. This is called organolithium, makes sense? Organometallic compound, and this is just like Grignard type reaction, okay? We have done already the Grignard one. I have uploaded the video about the Grignard one, so you can watch that one. I am going to skip the Grignard reaction here, okay? I think I have done already as well with one example. So you can see this is a carbon one, this is negative, which is a nucleophile. You can see here this negative, which is a nucleophile. So nucleophile is going to attack on the electrophilic carbon, O minus, and then protonation, so alcohol. Now Wittig is very, very important. Look at here. The very first step we are going to use triphenyl phosphate, PPH3. So triphenyl phosphane, I made mistake, sorry. So PPH3 have a lone pair, so it will act as a nucleophile and we have alkyl bromide. So first of all, we are going to make a phosphorus gylide for the Wittig reaction. And what is the formation of phosphorus gylide? If you are going to react PPH3, triphenyl phosphine, with alkyl halide and the reaction type is like SN2 in this way, I think I should discuss in this way. Look at here. Suppose we have this CH3CH2Br and we are using this phosphorus triphenylphosphine, this one. So the reaction type is SN2. What is SN2? SN2 means nucleophile attacks on this carbon and bromine leaves. So as a result of it, we have CH3, CH, H, and here P plus, PH3, clear, like this. Okay, now this carbon has a hydrogen which is very acidic. This one, either top or bottom, it doesn't matter, and we are using a base. So base is going to grab this proton, so there is a negative over here. So CH3, CH negative, and P plus PH3. So this is called phosphorus halide. We can keep a double bond here as well, because plus and minus is going to interact and it can form a double bond like this. CH3, CH double bond, PPH3, PPH3. Clear? So this is my reagent in Wittig. You can see here nucleophile is this one. Nucleophile is going to attack on the carbon electrophilic and bromine leaves. This is SN2. So base is going to grab this proton, and then we have this Wittig reagent. Clear? It can be plus minus form or it can be in double bond form. Now the next one, there is no need to know the mechanism. There is no need of it. You should know the direct conversion. Look at here how we can convert them. Look at here. Suppose we have this compound and we are using here like this, CH3, CH double bond, P, PH3, okay, in this way. So simple thing is that whenever you have such a type of reaction, always write your ketone molecule or aldehyde, and then you should write the phosphorus part close to the oxygen in this way. P, PH3, double bond CH, CH3, in this way. Clear? And simple thing is that you have to remove this oxygen with PPH3. Clear? And once you are going to remove this PPH3 with the oxygen, it will be like this, double bond CH and CH3, and the byproduct will be what? POPH3, P double bond O and 3 PH ring. PH means benzene ring, okay? This is the product of this reaction. Clear? We can discuss few more examples. Suppose you have this one. Again, I said that write down the aldehyde part in this way, and this close to this oxygen, P, PH3, double bond, and this carbon is bonded with this carbon, and there is two more connectivity. So remove this oxygen with this. Clear? And what should be the direct product? Look at this carbon having a hydrogen, and then we have a double bond with this carbon, and this carbon bonded with another carbon having 2-methyl. Clear? So this is my product, and you can see this is showing geometrical isomer, which means ENG cis and trans. Generally whenever we have a middle double bond, like this, not terminal one, terminal cannot show geometrical. So whenever we have isomer in this form, so we can convert the structure in cis and trans or ENG. Generally trans is more stable than cis form, or E is more stable than G. So you have to convert the structure in the E form. Clear? So there is a hydrogen as well. So how can you decide ENG? With the priority. So left hand side this carbon is number 1. In this side this carbon is number 1. So you can see both double bonded part like this, and here we have the ring, and here hydrogen. So you can see this is my E alkene. So this is the most stable product of this reaction. Clear? So this is about the Wittig one. So this is all about the carbonyl reaction, in which we have covered most of the reactions of aldehyde and ketone, and this is all about the DAT. So what we have done today, we have done the structure of carbonyl, like sp2 hybridized, oxygen is more electronegative, so CO bond is a polar bond. And then we have done the nucleophilic addition reaction, and I told you that nucleophile is going to attack either top or bottom. And after that we have done oxidation and reduction, and then we have done organometallic reactions like organolithium, and I have done the Grignard as well, and we did Wittig reaction, which is very, very important. So this is all about the carbonyl, aldehyde and ketone reaction. So thank you so much. Please watch this, write down everything in your notes, revise every day, and please share and subscribe with your friends, and I'm just looking for more subscribers. So thank you so much for watching this.